Now we're going to get into the topic of isotopes. What are isotopes? Isotopes, I've got the definition here for you guys. Isotopes are atoms of an element that have the same number of protons and electrons, but different number of neutrons. So they have the exact same atomic number always because it's the same number of protons. And remember, it's the atomic number that determines what the element is. So they have the same number of protons, but you're going to notice that their atomic masses or their mass numbers are always going to be different. Okay, how do these isotopes compare? Well, they end up having the exact same chemical properties. So the isotopes of an element have the same chemical properties. And the reason for that is that chemical properties are going to be determined by the number of electrons. And the number of electrons are exactly the same in the isotopes. Their physical properties differ slightly. Because they're going to have different masses because they have different neutrons, different number of neutrons. So that's why the physical properties are affected, but not the chemical properties. Okay, let's talk about some examples of isotopes. And I have them down here. Can you see this? This is a boron, B and B, they're both borons. How do you know that they're the same element? Because they both have number 5 here. 5 is the atomic number. Lower left hand corner, remember, of a nuclide symbol is the atomic number. If you look at the periodic table, you're going to see boron over here, boron, and the number on top is a 5. Okay, and that's why the lower left is a 5. But look at the difference. This boron has an atomic mass of 10. This boron has an atomic mass of 11. So that means this one has 5 neutrons and this one has 6 neutrons. These two borons are isotopes. Here are 2 lithium isotopes. Look at this. You can tell they're both lithiums because I put an Li and Li, and they both have the atomic number of 3. So if you look at your periodic table, the number on top in the periodic table over lithium is 3. That means each one of these lithiums has 3 protons and 3 electrons. But look, their atomic masses are different. So that means that the number of neutrons are different in these 2 lithiums. This one, 6 minus 3, this has 3 neutrons. This one has 4 neutrons, okay? Down here, you're going to see 3 hydrogens. Look at this, 3 hydrogens. Hydrogen, hydrogen, hydrogen. Hydrogen has 1 proton, 1 electron, 1 proton, 1 electron, 1 proton, 1 electron. This hydrogen here has an atomic mass of 1. So if you go atomic mass number minus atomic number, 1 minus 1 is 0, that means this one has 0 neutrons, no neutrons. The majority of hydrogen in the world is this. Hydrogen typically, all the hydrogen in the universe has typically 1 proton, 1 electron, no neutrons. But there are isotopes of hydrogen. This is called deuterium and this is called tritium. This hydrogen has 1 proton, 1 neutron. This hydrogen has 1 proton and 2 neutrons, okay? Look at the 3 carbons. These are 3 isotopes of carbon. This carbon, 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 all 3 of them have an atomic number of 6, 6, 6. That means 6 protons, 6 electrons, 6 protons, 6 electrons, 6 protons, 6 electrons. But this one has an atomic mass of 12. This has an atomic mass of 13. This has an atomic mass of 14. You may have heard of carbon-14 dating. They use that radioisotope to figure out how old a fossil is or stuff like that. But anyway, so carbon-12, carbon-13, carbon-14. How do they differ? They differ in the number of neutrons. So this one has 6 neutrons, this one has 7 neutrons, and this one has 8 neutrons. Okay, now I want you guys to look at your periodic tables and look at the masses that they have, let's say under boron. Remember how I told you guys that there were 2 isotopes for boron, boron 10, boron 11. Well, look at the mass that they have here. They have 10.81 AMUs. So the mass of Boron is 10.81 AMUs. Well, that's not the average, is it? Because if this was an average, it would be 10.5, right? But it's 10.81. So where do they get that from? Well, it's not a typical average. What they do is they take something called a weighted average. What that means is that they take into consideration the abundance of each isotope. Let's take a look at the carbons, for example. If you were going to average 12, 13, and 14, what would you get? You'd get 13. 12 plus 13 plus 14 equals, and then divided by 3, you would get 13. But take a look at the periodic table. The atomic mass is 12.01 AMUs. So that means they've weighted it, they've weighted the average, taking into consideration which one of these carbons is the most abundant. So if you take a look at this 12.01, which one of these 3 carbons would be most abundant? Obviously, this carbon 12 must be the most abundant. And I'll give you the percent abundance in a little bit. All right, back to the boron scenario again. All right, 10.81. What number is closer to 10.81? 11 or 10? 11. That means we have more boron 11 than boron 10. All right, so let me write down some of these percent abundances and show you how they actually get to that weighted average. So you're going to need to know how to do this type of a calculation. And your averages are all on the periodic table, but your percent abundances are in your book. So let me just do boron for you guys, and then you can practice with some others. So there were two borons, boron 11 and boron 10. Number lower left-hand corner is a 5, right? Why? Because boron has 5 protons, and that's its atomic number. So the mass of boron 11 is 11.009 AMUs. Okay. The mass of boron 10 is 10.013 AMUs. These numbers will be given to you guys. All right. Now, the percent, remember how we said 10.8 is closer to 11, so that means boron 11 must be more prevalent, and that is absolutely right. Boron 11, 80.4% of all the boron in the world exists as boron 11. And then the rest is going to be boron 10. That is 19.6% of all the boron in the world exists as boron 10. Okay, and if you look in the chart in your book, I just shut the book. But if you look at the chart in your book, it will tell you the percents of the different isotopes. So if you look at, oh gosh, I just had it open a second ago. I'll show you which one I'm talking about. And for those of you who have the ebook, it should also be there. This chart over here, this one. Okay, so it's got all of the ones. You don't have to memorize this, obviously, but you need to, if I give you the atomic masses and the percent abundances, you should be able to do the following calculation to figure out the weighted average of isotopes. All right, so what do you do for this thing? Take my glasses off. Percent means divided by 100. So you get rid of this percent sign and you move the decimal 2 places to the left, which means what percent is. Because like basically, if you had an 80% on an exam, that's 80 divided by 100, 80 out of 100. So 80.4%, just divide by 100. So you take this first one and you go 11.009, and then you multiply it by 0.804. Just move the decimal 2 places to the left. So get our calculator. Notice this is 3 sig figs and this is 5 sig figs. Now from now on, you've got to pay attention to sig figs. You don't, in a problem, they're not going to tell you, hey, by the way, remember round to the right number of sig figs. Because you've already done that chapter where sig figs were introduced, now it is assumed that you know how to do sig figs from now to the end of the semester. Okay? Don't ever leave a number in lab or in any other scenario where you've got a ton of numbers without rounding it correctly. So for the exam, for any practice quizzes, for labs, always, always, always pay attention to sig figs. So back to this. 3 sig figs, 5 sig figs. Final answer has to be 3 sig figs. So let's do the math. 11.009 multiplied by 0.804, and you get 8.851236. I'm just going to round it to 3 sig figs, which is 8.85. Now, I do the second one. 10.013 times 0.196. Remember, we're moving the decimal 2 spots to the left. You have to do that for any calculation you're doing for isotopic abundance, or when the question is saying, what is the average mass of this element? Or use the isotopes and the masses of the isotopes to figure out what the weighted average is. This is what you do. So I get my calculator and I write 10.013 times 0.196, and you end up with 1.962548. Round it correctly, 3 sig figs, that's what I have. All right, now this is the step a lot of students forget. What you need to do next is take this number and this number, add them together, okay? So we're gonna go 8.85 plus 1.96, and you end up with, remember, addition rules of sig figs, you go with the least number of decimal places. 2 decimal places, 2 decimal places, so your final answer has to be 2 decimal places, 10.81 AMU. And that is the weighted average of boron. And if you take a look at your periodic table, what do you see? Underneath boron, 10.81 AMUs. Okay, good. We'll move on to something else.